Hello everyone, welcome to the lecture today. In previous chapters in this course, we have seen that how to obtain analytical response of a single degree of freedom system subject to either for the case of free vibration or when the loading is harmonic or pulse type loading or step forces. But we'll encounter many cases in which the loading cannot be represented as a closed form solution. And even if the loading can be represented as a closed form representation, the solution cannot be obtained as a closed form analytical solution. So in that case, we have to rely on numerical methods to find out the response. And we are going to learn few of those numerical methods and see how to utilize those numerical methods to find out the response of a single degree of freedom system. Now, because this course only focuses on only on structural dynamics and not numerical methods, our discussion would be brief and we are going to discuss one explicit method, one implicit method, and feel free to explore more because there is a vast literature available on this topic. But I'm just going to show you illustration or examples of those methods, and it will give you an idea or a platform that you can use to further explore this topic. Okay, so let us get started.
In today's class, we are going to see how to get the response of a system, a single degree of freedom system, using numerical methods. So, if we consider our equation of motion, okay, that we have been dealing so far, is actually can be written like this, okay. And in the previous chapters, we have seen that PT, which is also the excitation function, okay, how to get the response ut for a given excitation pt, and basically we got this response for different kind of situation. Okay, so we got this where only the initial conditions were provided and no force was acting, so that was free vibration. Okay, so the motion was initiated by initial condition, and then we saw cases in which we had a force acting on the system. Okay, so in forced vibration, basically we saw different kind of forces. First we considered harmonic excitations. Okay, harmonic excitations in which the force can be represented as function of sine or cos. And then after that we also saw how to get response subject to different kind of arbitrary excitation, but for which we could define the excitation as a function of some time variable. So for example, step excitation or ramp or different kind of pulse loadings, we saw how to get the response. So half sine pulse or the triangular loading. Now for all these cases, we were able to get u, okay, analytically as a closed form solution of some function, okay, here. Now it might happen that we can encounter cases in which pt cannot be represented as some function, okay, or even if it can be represented as some closed form function, it is not easy to derive the solution for ut, okay, analytically. And for those situations, it is imperative that we study methods through which we can get the response even the analytical solutions are not available. Okay, so that's where the numerical response evaluation comes into picture. Okay, so numerical response evaluation would be utilized to get the response of this single degree of freedom system, or we are dealing here only with single degree of freedom system, but remember this can also be extended to multi-degree of freedom system. Okay, so we would get the numerical response using different methods, and we are going to talk about those methods. Okay, so let us consider PT. Okay, which is some arbitrary function, cannot be write as a closed form solution. Or even if we consider these cases here, many times these loadings that are represented as a nice, a smooth function of f are actually simplification of the actual loading. For example, a triangular loading is a simplification of a blast loading, for which the loading actually varies like this. Yes, it is not actually a triangular loading, but for many purposes, assuming or approximating the blast loading as a triangular loading gives us comparable results for, depending upon the response quantities of interest. Okay, so the question becomes how to get the response if pt. Okay, so let me just draw pt here. Okay, so pt, let us say, is given, okay, some random arbitrary variation. Okay, something like that. Now, subject to that pt, we will have some response, right? Okay, so let us say the response looks like this. Okay, let us say this is ut. So the idea is how to get from this point to this point. Okay, so our problem statement here is that if we have been given the equation of motion here, okay, if equation of motion is something like this, okay, now what I'm going to write down, my loading or the spring force as some function of u and u dot. Okay, just to emphasize that when we use the numerical methods, the utility for these kind of methods or the applications are not limited to linear systems. Okay, it can be extended to non-linear system as well. Okay, so in that case, my fs, what we have been assuming as k times u, okay, it need not to be like that. Okay, so we can consider non-linear system like bilinear or hysteretic systems as well. Okay, so just giving you a, what are the potential application. However, for the purpose of this course, we would limit our discussion to only linear systems. Okay, but numerical methods can be utilized to get the response for any other type of system as well. Okay, so let us say this is our equation of motion. Okay, so pt could be either an external force or it could also be ground excitation or support excitation, in which case it can be written as mass times the acceleration of the ground or the support. Okay, and these initial conditions are given. Okay, these initial conditions are given, basically u equal to, okay, let us say u0 and u dot 0 is equal to u dot of 0. Okay, so this is our problem statement. So let us first discuss the fundamental principle of numerical response evaluation. How do we do it? So for numerical response evaluation, what do we do? The given function, if it is given in a discretized form, okay, then it is fine. Otherwise, even if it is given in some continuous form, okay, remember, as I said, this is more useful for complicated functions. Okay, but it can be utilized for other in any type of function. It is not restricted to a particular set of functions. So what do we do? We represent our force in discrete values, okay, separated by simple time steps. Okay, so let us call this p0 here, p1, p2, and so on at time t equal to 0. Okay, t1, t2, and so on. And at any time, let us say it is step I. Okay, so the time is ti and the value is pi. Let us say after delta t, it is ti plus 1 and the force is pi plus 1. So pt actually we represent it as a set of discrete values. Okay, p1, p2, pi plus 1, and then pn. Okay, and our displacement, okay, need to be determined at the same instances of time. So basically u1, u2, ui plus 1, and let us say un. Remember, all of these are at time instances t1, t2, ti, ti plus 1, tn. Okay, so we discretized our excitation. Okay, and then we get the response as discrete values of the response at those points. So we don't get it as a function or a closed form solution, but for each time instance t1, t2, we get a value of u1, u2, okay, at those instances of time. So let us say this is t1, 0, t1, t2, this would be u1, u2, and so on. Let us say at ti and ti plus 1, I get as ti plus 1, I get my responses as ui and ui plus 1. Okay, so this is our goal here, that how from a discretized points that represents the excitation function, how from that we can get our response like this. And the way we do it, we employ numerical methods to calculate the response. So using these numerical methods, we can get the response like this. Okay, and basically our idea is that if we know the state of a system at time t equal to ti, so let us write down our equation of motion at time t equal to ti. Okay, it would be cui and then kui is equal to pi. Okay, if I have somehow found out the values of this parameter, okay, so the response parameter, acceleration, velocity, and displacement, and force pi is already given. Okay, we want to go from this step to the next step here. Okay, so we want to go to the next step here. Okay, all right, and this is basically called time stepping. Okay, so numerical methods are also many times referred as time stepping methods. Okay, and many places they are also called as integrators. Okay, so keep that in mind. Okay, so we want to go from this step to this step. So if somehow we can devise some numerical method which could assist us in getting the state of system from t equal to ti to t equal to ti plus 1, then I can get the response values at all instances of time. Okay, and if I can get my numerical response, then I can go ahead, get the peak response and get the other response quantities as well. So basically I would get set of data points representing my response here. Okay, and this is what our goal is. Okay, so through these chapters we are going to be discussing methods, okay, through which we can go from state t equal to ti, state t equal to ti plus 1, and through that we are going to obtain the response. Now the question comes, why there are methods, okay, not a single method. Okay, if a single method is there that can do the task, then why do I need multiple numerical methods? Well, it depends on many criteria. Okay, some of those criteria are basically when we get a numerical solution, unlike an analytical solution, okay, which is a closed form solution of independent variable, a numerical solution might or might not be accurate, it might not be stable, or it might not be convergent, and it depends on many parameters that leads to, okay, those criteria being satisfied. So the reason for having many methods, okay, some of those reasons I'm listing down here. Okay, so it depends on these criteria: stability, convergence, okay, and accuracy of the numerical response. Okay, so let us see what does it mean. Basically, stability means that, remember, in all these methods we basically go from one step to next step. Okay, and then we use a time step delta ti, which is ti plus 1 minus Ti. Okay. Now, a numerical solution is stable when decreasing the time step actually gives me a value that is going to a certain value. It might or might not be accurate. Okay. So the numerical solution should be stable, okay, in the presence of any kind of round of errors or anything like that. Okay, the solution should not be fluctuating. Okay, so if my actual solution, let us say analytically I have it obtained, the actual solution is like this. Okay, stability means that there might be inaccuracy like this. However, the solution is still stable. Okay, however, if I get a solution like this, okay, that means the solution is not stable. Okay, so stability means that it is basically giving me a realistic value, not fluctuating. Okay. Now, second thing is convergence. Convergence means that when I decrease the time step delta Ti, then my solution should approach to a particular value at each and every time instant. Okay, so that what convergence means. For example, if I decrease my time step, then it should move towards a fixed value. So if I decrease my time step, my solution U should move towards a fixed value, okay, which might or might not be an accurate value, but it should at least converging towards that value. Okay, and that's why we have accuracy. If the value towards it is converging, okay, is equal to the analytical solution, okay, it's an exact value, then we say that my solution is actually accurate. Okay, so in terms of basically numerical solution, these three conditions might not always be satisfied. Okay, so that's why we require, okay, different numerical methods which can provide appropriate stability, convergence and accuracy for different kind of or different scenarios. Okay, and you will see that some methods, numerical methods, work better in certain situation, and certain other numerical methods work better in some other situations. Okay, so this is from the point of view of stability, convergence and accuracy. But there is one also other point which plays a big role, and that is computational cost. Okay, so remember, each of these numerical solutions, when they are determined, okay, computer has to perform certain number of operations to obtain the solution. Okay, and how efficient a computational solution is, it depends on the algorithm for that particular method. Okay, so some method might be computationally very efficient, okay, and it might be utilized in certain scenarios, okay, but you might have to give up on certain other features like accuracy. Okay, so that's why different numerical methods are utilized so that computational time is manageable, okay, with some expectation on the accuracy of the solution. Okay, so these four criteria determines which method or which numerical method to evaluate the response are better. Okay, all right. If that is clear, let us move to our first numerical method, which is interpolation excitation method. Okay, interpolation excitation method. Now, in an interpolation excitation method, as the name suggests, if I have the system like this here, okay, what I do, I take the function ft or pt, okay, and then let us say this is the time variation and this is time t equal to ti. Okay, so let us say this is state I and this is state I plus 1. Okay, I draw a straight line between two states. Let us say this is pi and this is pi plus 1. Okay, so we discretize our excitation in the interpolation excitation method. Okay, so if our system is linear, okay, this only works for linear system, and this is popular because it is computationally very efficient. So if the system is linear, I don't have to go and use like complicated numerical methods. Okay, if my only issue is that my pt cannot be represented in terms of closed form function, or subject to pt my u value cannot be determined, okay, as an analytical solution, then I can utilize this interpolation excitation method for linear systems. Okay, and then it is a very computationally efficient method. So let us say, what do we do in this method? Given the state I, okay, I interpolate my function, excitation function between pi and pi plus 1. So let us say I define a time variable which starts at states I, okay, and goes up to I plus 1. So that tau here represents, okay, the time variable between this and this. Okay, now this total time step is delta ti, that is already known to me. Okay, so p tau, which is at any time tau after the time step I, can be written as, okay, pi plus delta pi divided by delta ti times tau. This is the interpolation of the excitation function. Okay, so my equation of motion that I need to solve becomes, okay, remember delta pi here is nothing but pi plus 1 minus pi, and my delta ti is ti plus 1 minus ti. So my equation of motion becomes as mu double dot plus ku, that should be equal to pi plus delta pi divided by delta ti tau. Okay, and I'm first considering undamped system, but same procedure can be extended to damped system as well. Okay, so this is my equation of motion subject to initial condition. Remember, my variable tau is starting at time I. Okay, so the initial conditions are basically conditions given at u of I, okay, and u0 is u of dot velocity is at I again. Okay, so the initial conditions are provided at the start of this variable tau. Okay, so the total response, can I say, remember, I'm trying to find out response subject to this. This is my excitation function. So this can be represented as response due to initial condition plus response due to this plus response due to, let me just rewrite it again. Okay, so it is the sum of response due to this plus, so a step function, then a ramp function, and plus the initial condition, okay, that was acquired up to the step I. This is very important. You have to remember, my system is not starting from rest. There would have been some initial condition up to step I. So I need to include that. Okay, so the total would be sum of response to all this solution, and it can be written as u tau, okay, as equal to first the initial, okay, free vibration due to initial condition. I can write it as ui cos omega n tau, okay, plus velocity term here, okay, sine omega n tau, and then the response due to the step function here, which we have already derived, is given as the value of this one, which is, okay, delta pi divided by k, okay, tau delta ti minus sine omega n tau divided by omega n ti. Okay, this is due to ramp function. Okay, this is due to the loading due to this linearly increasing phase. Due to a step function, let me write it, it would be pi by k 1 minus cos omega n tau. Okay, so the total displacement can be represented as sum of displacement for each of these combination, and I could do that because it's a linear system, so the principle of superposition is valid. Now I can go ahead and I can differentiate this, okay, and I can get certain expression. Okay, the next thing that I need to do, remember what I want, given the state at I want to go to I plus 1. So what do? I substitute my time variable tau equal to del ti. Okay, when tau becomes del ti, remember if you look at here, when tau becomes del ti, I basically reach to step I plus 1. So u of tau becomes ui plus 1. Okay, u dot of tau becomes u dot I plus 1. So that is I'm going to do in the expressions that I have obtained here. Okay, that I will get my ui as some function here and ui plus 1 as some function here, which would be in the, okay, in terms of known parameters, okay, of I, known parameters in terms of, okay, previous steps. Okay, and then so remember this would be ui plus 1, this would be u dot I, velocity, displacement and velocity at step I plus 1. Now these can be arranged, okay, these can be arranged and the solution can be written in this form here, some constant times ui plus another constant times, okay, and you can actually derive that and see what are those constants. Okay, it's not very difficult to do. Okay, I'm not deriving it here so that not to get bogged down by with all the equation and mathematics here. The important thing is to understand the concept here. Okay, so it would come like something like this. Okay, ui at the previous step, velocity at the previous step, force at the previous step, and force at the current step. But remember, I already know the force at the I already know what is the force at the current step. In fact, if the excitation is given to me, which according to this problem, okay, then my force values is, it's like they are known at all the time steps. Okay, similarly, my velocity would be another constant which is different from this. Okay, in terms of ui plus ui dot and then pi, and then again another constant times pi plus 1. Okay, so although we have derived this for the undamped system, the general form of this equation is going to remain same even for damped system. Okay, so both, this is the equation. Only thing that is going to differ that these constants are going to be different, and you can refer to any textbooks to have a look at what these constants are. These constants basically depends on the structural property of the system, so it would depend on the time period, frequencies, damping, and also the time step in the system. Okay, it won't depend on any other parameter. Okay, so these parameter, these constants would need to be calculated only once. Okay, at the beginning, okay, at the beginning of when the motion starts. Okay, with the initial condition, of course, that is given to us. And once that is known, I can utilize, right? I can utilize these expressions to go from step I to I plus 1. And then I won't keep on repeating that. Now know that we have obtained displacement and velocity here. Acceleration, we can either differentiate and obtain it, or if you consider the equation of motion as this, okay, you can get the acceleration at step I plus 1 once the displacement and velocities are known to us. Okay, so if these are known to us, which in fact they are, I can get, remember these quantities are known, then we can also get the acceleration. Okay, so generally what do? We program it in some sort of mathematical programming software. So you can use like MATLAB, you could utilize even Excel, or you can utilize like Python or any other language of your choice. Okay, and you can put this inside a for loop, a loop that actually goes up from over a certain values, certain iteration, and then you can get the response. So basically, given it will start with some initial condition, and then basically this is the response you'll get the discretized points. Okay, and how closely these points are separated? Okay, those depends on the time step that you choose. Okay, so we have considered a constant time step, but remember it doesn't have to be. Even that if the time step is changing, you can still find out utilizing the same method. Only thing is that in that case, all these constants would need to be calculated at each and every step. So this would be changing, because if your delta t is changing, then these constants would be changing. Okay, so this is called interpolation excitation method. Okay, interpolation excitation. Okay, or other way around, sorry, excitation interpolation method. Okay, which is useful for linear system. Okay, because it is computationally efficient and works quite well for the linear system. Okay, but I mean, that might not be sufficient, because in reality we would encounter many systems that are non-linear, and I would want to have a method that could be used for linear as well as non-linear system. So from that perspective, we are going to study two additional numerical methods that can be universally utilized whether the system is linear or non-linear. Okay, the first of these methods that we are going to discuss is called central difference method. Okay, it is called central difference method. Okay, now a central difference method, okay, it is basically based on the finite difference approximation of the time derivatives of the displacement, velocity and acceleration. Okay, now you might already be aware that given displacement value, let us say ui, okay, and ui plus 1, if I have to find out, and let us say these are separated, okay, these are at time ti and ti plus 1, so separated by delta ti, which is equal to ti plus 1 minus ti. So if these points are given, because velocity is basically the slope of the line joining these 2 points. Okay, so if you want to approximate the velocity, okay, approximately calculate the velocity, it would be simply slope of the line joining these 2 points. So I can write down my ui dot as ui plus 1 minus ui divided by delta t. Okay, and acceleration would again be, okay, acceleration can be written as, okay, let us call this y plus 1. It can be written as velocity, okay, divided by delta t. All right, so this is the concept that we extend in central difference method. Okay, so what do we do in central difference method? Okay, we first consider velocity, okay, joining the displacements which are apart by 2 delta t. So instead of just consecutive points, I can also say that I would write my velocity ui as ui plus 1, then ui minus 1. And now remember, these points are now separated by 2 delta t. Okay, because there are 2 steps in between. So the slope joining these two would be 2 delta t. And the reason why I'm considering, like, 2 steps apart, it would clear when I write the acceleration. Remember, by default, if I try to express my acceleration here, okay, as ui dot, and then let us say, or let me write this as ui as, okay, so this is the acceleration I'm trying to find out, which will be derivative of velocity. Okay, let us say it is this same expression that I have just used above. Okay, so I can further substitute my ui dot from the expression here. Okay, and I can write this as, okay, I can go ahead and I would write that expression as ui plus 1 minus ui divided by delta t, and minus ui minus ui minus 1 divided by delta t, and this whole thing would be multiplied with 1 by delta t, which is the denominator here. Okay, so we can arrange it and we can write down our acceleration as, okay, ui plus 1 minus 2 times ui plus 2 ui minus 1 divided by delta t square. Okay, so what I have done here, okay, I have written down my velocity and acceleration, which are time derivatives of the displacement. Okay, I have written down as simply as an expression of displacement. Okay, why is it necessary? Well, if I have that, then the differential equation that I have, which is this, okay, the differential equation that I have, okay, all the derivative terms can be removed if I substitute this and be written in terms of only displacements. Okay, and that becomes very useful to us. Why? We will see now. Okay, so I'm going to write this here as ui plus 1 minus 2 ui plus 2 ui minus 1 divided by delta t square. This is my acceleration. Then cs and ui minus 1 times 2 delta t, then plus k ui, and this is pi. Okay, so the way I want to arrange this equation so that I can write it as some constant times ui plus 1 is equal to some functions which are known on the right hand side, so that if this coefficient is known and the functions on the right hand sides are known, then I can find out this value. Okay, and which basically means given the state of the system at I can find out the state of system at I plus 1, because once ui plus 1 is known, then I can find out ui dot plus 1 and then u dot I acceleration using the expressions that we have obtained here. Okay, so basically that is our goal. Okay, from this expression how to get that. So if you rearrange this, what you will see, this can be written something like m divided by delta t square plus c divided by 2 times delta t. Okay, and this ui plus 1 should be equal to pi minus delta t square minus c by 2 delta t, and then it is multiplied with ui minus 1, and then I have the second term here, or say third term here, which is this. So if you rearrange this equation, okay, that we have, we will get this. Now what I'm going to do, I'm going to write this as another expression, okay, which I will denote as, okay, okay, k hat, which basically some represents some sort of stiffness or the equivalent stiffness, and this is equal to pi hat. Okay, now if you look at these carefully, k hat depends on the mass and the damping on the system and whatever the time step that you choose. Okay, and if the time step is constant, this k needs to be calculated only once, not at each and every step. So if it's a linear system, okay, and the time step is constant, this k needs to be calculated only once. Similarly, on the right hand side, pi is known to me from the previous step, and ui minus 1 and ui, they are also known to me from the previous steps, and the other things are basically system properties that can be determined using the provided values. So I get my equation for the differential equation in this form. Okay, so that I can find out my ui plus 1 as pi divided by k hat. Okay, so in this one as well, given the state of the system at previous steps, I have been able to find out the response at the next step. Okay, now the initial condition would again be the same. Okay, it would be u0 and u dot 0. Now there is one issue here though. Okay, if I consider this equation, if you look at it here, okay, at I equal to 1, okay, let us say, if you consider in this expression, okay, at I equal to 1, or let us say I equal to 0. Okay, so that I'm calculating this k hat times u1, I'm calculating the first step. Okay, So with I equal to 0, this would become k hat times u1 equal to p of 0. And what would be the p hat, sorry, p hat 0? What would be p hat 0? It would be p0 minus this coefficient. This is minus u minus 1 here. And this is u0. Now u0 is known to me as an initial condition. P0 is known to me. Okay, the force at time t equal to 0. Okay. Question becomes, how do I get this? Because this is not known to me. Okay. So to get u minus 1, consider it to be another constant that need to be determined. Okay. And the way we find out using the initial condition where we write down u0 is equal to u1 minus u minus 1. I'm using the same expressions that we have used for velocity and acceleration. Okay, so I'm going to use the same expression here. All right, 2 delta t, and then u0 double dot is equal to u1 minus 2 u0 u minus 1 divided by delta t square. Now all the terms are known in this one except, okay, u1 and u minus 1. So we can solve this and find out u minus 1 as. Okay, because there are two equations, simultaneous equation, I can solve it and I can this get u minus 1 as u0 minus delta t times u dot 0 plus delta t square by 2 u dot 0. Okay, and then my solution becomes complete in the sense that I can now utilize this to start my iterations and get the response. Now remember how accurate the response would. So let us say I have found out analytically that response looks like something like this. Okay, now whether my numerical response, how close it would be to the actual response. Okay, it depends on many parameters, and one of those parameters are time steps that we use. Okay, so it can go something like this. Okay, it can follow like this. It is always discretized, is it not? Always discretized. Okay, so how accurate it is or how close it is to actual solution, one of those parameters that determines this is actually the time step. Okay, and central difference method is stable if it is satisfy this criteria. So if you have a single degree of freedom system, okay, my delta t by tn should be smaller than 1 by pi. Okay, if this condition is satisfied, then my solution would be stable. Okay, if I determine using the central difference method. Okay, and this condition basically comes from some stress velocity criteria, okay, which is beyond the scope of this course, but basically some condition need to be satisfied for this method to be stable. Okay, which is typically not a problem for the some general type of structures that are there in structural engineering, because we typically use time steps which are of order 0.01 or 0.005 like that. Okay, which would always satisfy this condition, because time period of a typical structure can be between 0.2 second to, let us say, 2 second or 3 second like that. Okay, all the time periods in this zone, this condition is satisfied very easily, because it would require delta t to be, okay, between 0.06, okay, to the value 2 by, okay, so it would be around 0.66, let us say. Okay, and that is not a problem. Okay, because typically the value that we use are satisfied, but remember the time period is for a particular mode, and here we are only considering single mode because it is a single degree of freedom system. But for multi-degree of freedom system, okay, many modes could be of interest. Let us say 10th mode, and as the mode increase, and you will see in the later chapter, the time period actually decreases. So depending upon your mode of interest, this condition might not be satisfied. So it might be problematic for multi-degree freedom system. Okay, so that need to be kept in mind. All right, so this was the discussion on central difference method. Okay, which is perhaps one of the easiest method that could be universally utilized for a linear and non-linear okay, systems altogether. The next type of method, okay, that we will discuss, okay, is called numeric method. Okay, so numeric method is another set of numerical procedure used to find out the response of a, okay, differential or response of a basic dynamic system. Okay, now numeric method, as we discussed in the central difference method as well, the idea is to find out variation of ui or the response parameter at I plus 1, okay, okay, in some sort of known functions. Okay, so that is the goal. Once we can find that out, then I can go from step I to I plus 1. Now what numeric method does, it assumes, okay, numeric methods assumes certain variations of acceleration, okay, between step I and I plus 1. Step I and I plus 1. And depending upon those variations, I get the variation of velocity and displacement. Okay, so let us see what those variations are. So in the first type of numeric method, basically, if I go from, let us say, step I, where the acceleration was ui double dot, I go to the next step, okay, I plus 1. Okay, so the first set of numerical, in the first set of numerical procedure, okay, it is assumed that acceleration is constant between the step I and I plus 1. So it is a constant value. And the value of that acceleration actually is, okay, the value of that acceleration is, let us say I represent in terms of variable tau. Remember, this one total is delta ti. Okay. And if I have to represent my acceleration for any point in between I and I plus 1, it would be simply a constant value, average of these two values. Okay, so I will write it as u dot of tau is average of ui of tau and then ui of tau double dot. Okay, so the acceleration is assumed to be constant. Okay, in the second set of, okay, in the second set of numerical procedure, what is assumed that, again, let me draw the step I and I plus 1 here. Okay, basically a linear variation of acceleration is assumed. So it is assumed that between the step I and I plus 1, my acceleration is not constant anymore. It is varying linearly between the value ui double dot to ui double dot plus 1. Okay, so in that case, again, let me say this is delta ti and I'm representing the time between, okay, I and I plus 1 is tau. So I will write my acceleration as, okay, ui, okay, times tau divided by delta t ui plus 1 minus ui. Okay, which is basically a linear interpolation between these two values. So the acceleration is varying linearly. Okay, so this is called linear. Okay, this is constant acceleration. This is linear acceleration. Okay, once the variation is known, I can go ahead and I can integrate both these expressions here to get the velocity as a function of tau, isn't it? So I can, if I integrate it, I will get it as initial velocity plus the constant average acceleration, okay, times tau. Okay, and here if I integrate it, I will get a velocity as velocity at I plus this times tau plus tau square by 2 delta t Okay, ui plus 1 minus ui double dot. Okay, now I know that when tau is equal to delta ti, then my u dot of tau or u of tau becomes the next step. It goes to the next step, so it becomes ui plus 1. So if I substitute it here, I can write that as u of ti or ui plus 1. The velocity is equal to ui plus delta ti. I am substituting tau as delta ti is equal to this. Okay, similarly, it can be done for the linear acceleration as well. I can write down my ui plus 1 as equal to ui plus delta t by 2 here, ui plus 1, and then this value here. Okay, which is sort of same as what we have obtained here in the left hand side. The velocity I follow the similar distribution. Okay, I can again go and then integrate these expressions for the velocity as a function of tau to get the displacement as a function of tau. Okay, and I can go ahead and write this as ui plus u dot of tau plus tau square by 4 ui plus 1, and then here it becomes ui. Okay, similarly for this, I would write my displacement as ui plus u dot of I tau plus u dot of I tau square by 2, and then tau cube, okay, tau cube by 6 times delta t times ui plus 1 minus ui. So again, I'm going to do the same thing, substitute tau equal to delta t to get the next step response. So my u of I plus 1 becomes ui plus u dot of I delta t. Okay, this is delta t square by 4 ui plus 1 and then ui. Similarly, here I can get the expression as ui delta t plus delta t square 1 by 6 ui plus 1 plus 1 by 3 ui double dot. Okay, so what we have seen here, that given or assuming a distribution of acceleration between the step I and I plus 1, I am able to derive the expressions for velocity and displacement at step I plus 1 as a function of velocity and displacement and acceleration at previous steps. Okay, now in this method, the first method is called constant average acceleration method. It is called constant average acceleration method. The second is called linear acceleration method. Okay, so this is called Newmark's constant average acceleration method, and again Newmark linear acceleration method. Now, the expressions that we have obtained for velocities here and displacements here can be written as a combined expression in terms of some constants, and depending upon values of those constants, I can either get this constant average method acceleration method or linear acceleration method. So if I write down my velocity as ui plus 1 dot is equal to ui dot plus 1 minus gamma delta t, and then gamma delta t ui plus 1. Similarly, I would combine both these expressions and write down my displacement as this expression here. All right. this expression right here. Okay, so I have now written in terms of constant gamma and beta. Okay, and what happens when gamma is equal to half, okay, and beta is equal to 1 by 4, these expressions transform to the expressions that we have obtained for constant average acceleration method. Okay, average acceleration method. And if I utilize gamma equal to 1 but beta equal to 1 by 6, then I get the same expressions for velocity and displacement as linear acceleration method. Okay, linear acceleration method. Okay, so in general, Newmark's method, numerical procedures are written like this, in which, okay, we assume certain variations of acceleration, and then we get these expressions here. Okay, now if you look at carefully here, okay, the velocity and displacement at step I plus 1 depends on the response parameter at the previous step, but I also have these parameter here, which are basically acceleration at the current step. Okay, so remember, unless I can write down the expression such that my current step can be calculated wholly based on the previous step, okay, I would need to use iterative method to solve Newmark equation. Okay. However, if the system is linear, for that special case, okay, there is non-iterative Newmark method. Then I don't have to iterate it because I can solve the system for ui plus 1 and then substitute it in the equation of motion. Okay, so only for linear system I can use, okay, non-iterative Newmark method. Okay, so for linear system, all I need to do is basically write down my equation of motion at the step I plus 1 and then substitute all the variations that we have obtained. Okay, the expression for ui plus 1 dot and then ui plus 1, okay, displacement, okay, whatever the expressions that we have obtained here. And when we substitute it and eliminate ui plus 1 double dot acceleration at the current step, then I can write down my expression again in the similar form that I have obtained for, okay, that we had obtained for central difference method. So for Newmark method, I also get an again expression like this. Okay, where again k is some function of system parameters and pi plus 1 is again system of, or like, expressions of known parameters from the previous steps. Okay, so through this we can calculate ui plus 1. Okay, if ui plus 1 is known, then ui plus 1 dot can also be found out, and then the acceleration can also be found out either using these expressions here, or we can just utilize the equation of motion and write this as pi plus 1 times cui plus 1 times kui plus 1 divided by m. Okay, and then we keep iterating, okay, going from step I to I plus 1, where I varies between 0 to n, or the steps that we are of interested. Okay, now if you look at here, there is an important difference between the central difference method, okay, and Newmark method, okay, and the Newmark method. If you remember, in the central difference method, even to get the response parameters ui plus 1, ui plus 1 dot and ui plus 1 double dot, okay, we never utilized the equation of motion at I plus 1. The equation of motion that we utilized was actually this. Okay, this is the equation of motion we utilized, and we arranged this, substituted the term, and then wrote as k hat times ui plus 1 is equal to pi hat. Okay, so if you look at, let us go back where we discussed central difference method, and let us see what is the equation of motion we utilized. Is this step I or I plus 1? So even to get the value of the response parameter at the next step, we never satisfy the equilibrium equation at the next step. Okay, we got everything from the current step. Okay, and the next step was just found out using the previous step. These kind of methods where the state of the system is actually obtained wholly from the previous steps. Okay, it is called explicit methods because it is explicitly determined from the previous steps, and the equilibrium at the current step is not utilized. However, in Newmark method, if you look at it, the equilibrium at the current step was utilized, and that must be satisfied to get the response at I plus 1. These kind of methods are called implicit method, where response at step I plus 1 is determined using the equilibrium at I plus 1. In this case, response at I plus 1 is determined using the equilibrium at I. Okay, so these are also popularly referred as explicit methods and implicit methods of numerical procedure to get the response. Now we saw that for a central difference method, the criteria for stability was delta t by tn should be less than 1 by pi. Now for Newmark method, okay, again similar procedure can be followed that was followed to determine this, which we did not discuss. Okay, so that it can be discussed considering the stress propagation theory. Okay, but finally we get this condition for stability. Okay, now Newmark method is stable if delta t by tn is actually less than equal to 1 by pi root 2 times gamma minus 2 beta. Okay, if this condition is satisfied, then my Newmark method is stable. Now, if you consider constant acceleration method, okay, what was the value of gamma? Equal to 1 by 2 and beta 1 by 4. And if we substitute this, we get here as this term becomes 0. So this becomes infinity. So delta needs to be smaller than infinity, which would always be the case. So that's why the constant acceleration, average acceleration method is unconditionally stable. Okay, so it is always stable. Okay, doesn't matter what is the value of delta t. Okay, however, it might only be accurate. Remember, there's a difference between stability and accuracy. So it might still be stable, but it would only be accurate if delta t is very small. Okay, now for average, for the linear acceleration method as opposed to constant average acceleration method, so for linear acceleration method as well, we can substitute the value of gamma equal to half and beta is equal to 1 by 6. Okay, so delta t by tn, we get this criteria as 0.551. Okay, so this must be satisfied for the solution or the response to be stable, and for most of the systems actually this is not an issue. Okay, so this is satisfied for the civil engineering structure, okay, for most of the cases anyway, okay, considering typical values of properties of the structures. Okay, the issue here is accuracy. Okay, so while they might still be stable, but for to be accurate, the delta t has to be sufficiently small. Okay, and usually what happens whenever we utilize these integrators, we perform some analysis to see, we do some sensitivity analysis to find out if the delta t that I'm using for the analysis is small enough that it is stable and it is converging towards an accurate solution. So remember, I used all three properties that we discussed, that it should be stable and it should be converging towards an accurate solution or the accurate solution. Okay. All right. So these are the three typical, numerical procedures that are used, and there are so much of additional things to learn for these type of methods. Stability, convergence, all those things. You should recognize that there are a lot of material that can be studied for this topic. However, we would limit our discussion only to these three just to get an overall idea. What you can do, you can go ahead and you can try out some of the excitations that we have already considered. For example, harmonic excitation like this. Okay, consider some typical values of the properties and the excitation. For this, we already know analytically what is the response. So we know the exact response, okay, from the solution of differential equation. But you can employ the interpolation method, excitation interpolation method, or central difference method, or Newmark method, and then compare the response. Okay, compare the response for different values of the time steps and see how accurate they are. Okay, all right. So with this, we conclude our chapter here today. Thank you very much.